right, this is from 4-3. Hope you're getting used to this bar with the cylinders hanging from it. Now we have the same old bar, but the peg is through hole D, which means with no masses attached to it, this bar should be in rotational equilibrium. But no, we have set a mass in hole G, okay? It's not in equilibrium and it's free to rotate about the peg in hole D. Part A says 2 additional cylinders identical to the one shown can each be hung on the bar by hooks from any of the open holes so that the bar will be in rotational equilibrium when all 3 cylinders are hanging. So let's figure it out here, okay? We need the net torque to be equal to 0. What we have here in this initial state here is we have, if we just call the mass of the cylinder M, we have mg times 3 holes. So we got to balance out 2 cylinders, and how are we going to do that? So you can guess and check this, but intuitively you know that you don't want either of those cylinders in E or F, because G is the maximum amount of torque you're going to get on the right-hand side there. So we're going to have to do something clever on the left. Now, we know if we put one at A, then that's going to balance things out. So then I'm out of luck because I can't put that third one anywhere. So it kind of leaves us B and C. But remember, our unit of measurement here is 3 holes. So we need a total of 3 holes here. So what we can do is we can put 1 at C, and then the torque there will be mg times 1 hole. And we put the other one at B, and that gives us the net torque of mg times 2 holes. Both of those are going to work in the counterclockwise direction. This is going to work in the clockwise direction. So there we are. So we get 1 point for identifying B and C as the correct answer, and then 1 point for referencing to the fact that we need torques to balance. All right, part B, we take those additional 2 weights away and we return to our initial condition here with the weight in hole G. The bar is released and its resulting angular acceleration is recorded. Then we take the weight off and replace it with a string as shown, and we're gonna give a downward force of magnitude F equal to the weight of the hanging cylinder exerted on the string, and the resulting angular acceleration is recorded. Part B asks if the magnitude of the initial angular acceleration of the bar cylinder system in case 1 is larger, smaller than, or equal to the magnitude of the initial angular acceleration of the bar in case 2. And we're going to talk about our paragraph wording here. So the answer is that acceleration is larger in case 2. Right? Why is that? Well, we're dealing with Newton's second law in all of these cases. Now, the torques are equal. Tau 1 is equal to tau 2 because the forces are equal and the distances are equal, okay? But remember that the torques are equal to I alpha. This is kind of like what we did before. So again, which system, is going to have the greater moment of inertia? Well, case 1, we've got the bar and the weight, and in case 2, we only have the bar. Now, I don't know how to calculate, at least off the top of my head, the moment of inertia of case 1 or case 2, but I know that adding this weight far from the center of mass is going to increase that moment of inertia. So my moment of inertia in case 1 is larger, my moment of inertia in case 2 is smaller, but what I really care about are the angular accelerations, which are going to do this. So we have the angular acceleration larger in case 2. So how are the points given for this? 1 point for the right answer, 1 point for saying that the torques are equal in each case, 1 point for saying that moment of inertia is lower in case 2 or higher in case 1. It doesn't matter what you say. 1 point for using tau equals I alpha, and then 1 point for your paragraph structure. So 5 points for part B. Part C asks, during the collision, is the kinetic energy of the clay bar system constant? The answer there is no. This is an inelastic collision, so there's a loss of kinetic energy. Okay, even though being dropped there, it's not going to rotate, right? It's dropping right on the center there, but the lump of clay has kinetic energy before the collision. It's going to come to a stop, and it's going to have no kinetic energy, so it's lost there. You can get that point just for saying kinetic energy is lost in an inelastic collision. So that's part C. And part D asks about angular momentum. Is it constant or not? Well, you can reason this a couple of different ways. You can say that there's no angular momentum before the collision. Nothing's rotating and the ball is moving along the axis. And there's no angular momentum after the collision because, again, it won't rotate. You could say it that way, or you could also say, since there's no net torque on the system, there's that angular momentum is conserved. So again, 1 point for the yes answer and an attempt to justify it, and then 1 point for either saying, well, the initial and the final angular momenta are both 0, so it was conserved, or no net torque on the bar. Either way, so 1 point for C, 2 points for D.